Welcome to TechNotes. In this edition, we're going to talk about things that it's not always the air conditioning. We want to be able to think outside the box. So I'm going to walk you through a troubleshooting example that I ran across about a week ago, and we'll see what we come up with. The problem is it's a 14-floor condo near a beach. It's in an extremely humid environment close to Miami. The indoor humidity is about 67% with the AC running almost nonstop. So, of course, the first thing people do is say, my air conditioning isn't working right. Most techs will say, the air conditioning isn't working right. So let's walk through the whole troubleshooting procedure. Okay, there's very high humidity. Did a quick inspection of the condo unit, found there are signs of extremely high humidity for extended periods of time. The picture we're looking at here is inside the equipment closet. It's just a hallway closet, slatted doors, and it's actually the return plenum itself. Okay, this is the bottom of the closet near the open return. We always want to start with the thermostat. Okay, you cannot troubleshoot a system properly if the thermostat is not calling for cooling and the indoor fan is running. If you cannot get the indoor fan running, don't even go any further. You have to troubleshoot that first. In this case, fan came on, equipment was already running when I got there, set for an indoor temperature of 60 degrees. Indoor temperature was 71. However, again, we had 67% humidity, and this is what these people have been living with. Do an initial equipment check. So after checking in with the customer and making sure system is operational, find the outdoor system. In this case, it's on a roof almost 8 stories, a little over, 8 stories above where the air handler is. Okay, equipment overall is in good shape. Quick walkthrough shows things have been maintained. Locate the actual condenser and take a look at the outdoor unit. Okay, check the model number. This gives you the size. In this case, when we look at the model number, okay, you can find most sizes of units right in the model number. Okay, in this case, there's 024. That's a 2-ton outdoor unit. Okay, it's AC only. Again, Lennox and everyone else has different nomenclature for their model numbers, but you can also find it. The other thing we want to do is we want to check for the acceptable FLA and RLA levels. Okay, so the compressor has a run amperage of 11.2 max, and the fan is at a 1.0. Okay, so now that's if the original fan and compressors in the unit. If something's been changed out to an aftermarket, you may have different type of equipment. Okay, you also want to check what the refrigerant is. Okay, on most equipment, it's labeled what the refrigerant type is, either 22 or 410A. Okay, and then you also have the design pressures. That doesn't mean much in most cases, but it's nice to know. So the first thing we're going to do after we take a basic look at equipment condition is we're going to check the compressor amperage. It should not be over the rated amperage. In this case, it's 7.14 to the 11.1. We're fine. Okay. If it is over, you have to find out why. Check the capacitors, check condenser air coil for proper airflow, and then we can get into the pressures. But check your compressor amperage first. Check your outdoor fan amperages. As with the compressor, we want to know if the fan motor is operating properly. Without good airflow, you cannot get good readings on the rest of the system. Okay, if the amperage is high, okay, higher than, for example, the 1.0 we saw on the data plate for this system, you have to find out why. Most often, there's a capacitor that's bad. And if it's not the capacitor, you have to start looking at the bearings of the fan. Okay, so you got to make sure you check that fan amperage. It tells you whether or not we're getting proper airflow mechanically. Okay, then we can finally look at operating pressures. Now, there's a very important note and an important point I want to make before we go on to the next slides. If you do not need to put gauges on a system, do not do it. In this case, I'm troubleshooting for a humidity issue, which has a lot to do with pressures and temperatures, and it's a pretty large pressure building, I made decisions to put gauges on. Remember, each time you put the gauges on or off a system, you lose refrigerant. Minimizing refrigerant loss if possible by using stub gauges or very short hoses. You should always use low loss fittings. Put the gauges onto the system. Put pipe clamp thermometers onto the lines as well. Okay, take outdoor air temps, wet and dry bulb. Both are important. Wait 10 minutes for temps to record properly. Okay, pressures are sort of instantaneous, but temperatures take a little bit longer for those pipe clamp thermometers to actually register. In this case, I'm using the Testo set of tools, so it's a Bluetooth connection to my phone. Okay, so what can we say about these readings? I am looking here, I have 143.6 low pressure, 582 high pressure. That high pressure is a little high if we go back to that design temp slide a few slides ago. I'll take a look at that in a second. Okay, my temperature on the suction line is 77.4. My temperature on the liquid line is 94.5. My outdoor temperature is 95.3. So I'm looking at basically 4 numbers here. Actually 5 numbers. Okay. But what can we actually say about this? Is it right or wrong at this point? Not really. You can't say anything just based on the outdoor readings. You have to have indoor readings. Okay, because a technician here could say this system is overcharged and not realize exactly what's going on. Remember, I have an 8-story line set here as well. Okay, it's very important to remember. This is not a short line set. This is a very long line set. So my high suction line temperature, I'm going to have a high suction line temperature, even if everything is working properly. Okay, I do have a slightly high evaporator temperature. It's at 50.4, but there may be more reasons to that. Now, the one thing we can look at is the approach temp. Okay, Lennox equipment likes to use approach temp to check for proper charge. Approach temp is the difference between the liquid line temperature, in this case it's 94.5, and the outdoor temperature, which is 95.3. However, in this case, the unit is in full sun, on a roof, in Miami. It's hot and humid. Also, the line set drops from the roof down 8 floors to the condo. The approach temp method doesn't always work. Don't rely on it by itself. So what can we determine from these outdoor readings? Condensing temperature is 145. Outdoor temperature is 95. The difference between the two is 50 degrees. I can determine I'm rejecting heat. Okay, am I rejecting enough heat? Probably not, but it has to do with the full sun on the condenser. So, without my indoor readings, I cannot determine a thing yet. Okay, that's it for outside. Clean up, put the covers on, move indoors. Start with a basic inspection of the indoor unit. By the way, I did block off serial numbers for customer privacy purposes here. That's what the blue square is. Look for anything out of the ordinary. Check the data plate for size. It should match the outdoor unit. Again, in this case, we're looking at the data plate, and there's an 024, which is part of the data plate. That tells me it's a 2-ton unit. You know what? I have a match. Check for the blower motor FLA or RLA. It's on here someplace. In this case, it's 4.1. It's listed right there. Check for rated static pressures. Okay. When we look at this, there's a static pressure reading on here someplace, and it's going to be a 0.4. Next thing, easy first. Keep it simple. Check the filter for cleanliness. Look for airflow patterns. Look for the proper fit. Feel the airflow as you pull the filter. If the system's running while you pull the filter out, you can feel how hard the air is pulling against that. Now, I have a relatively large filter in here. But if you look at this, my airflow seems to be very concentrated to one portion of that filter. Is it the correct size? Well, still have to determine that. But it's not an even airflow straight across that filter. So my air is really just in the center of that. Take a look at the evaporator coil while you have the filter out. You can use a cell phone picture or something to look up into the evaporator. Is it clean? Does the drain pan look like it's leaking? Now again, the drain pan is going to be around the outside edge of this, okay? This is a plastic drain pan or a vinyl drain pan, and you want to look for anything that looks like it has holes. Is it rusty if it's metal? Look for leaks in the coil. Oil is a key sign of refrigerant leaks. Okay, look for leaks. What's the overall condition of the unit? Is the unit clean? Is there mold, mildew, or dirt? I show you better in another picture, but you can see that there's definitely been moisture in this system when you look at the labels. But overall, system's clean. Okay, I don't see much buildup on any of the metals. It looks like it's been taken care of. What type is the blower motor? Is it an ECM blower motor, or does it have a capacitor which has a typical 3 or 4 speed or single speed motor? Okay, again, here look at this buildup that's on look at the signs of moisture that's on this label. You cannot say mold or anything because you don't know what it is. Mold can only be identified with laboratory tests. ECM motors matter. Okay, they self-regulate for airflow. Okay, a lot of them are designed for specific static pressure, specific amperages, and they will self-regulate. Okay, we're still going to verify this, but overall, ECM motors do adjust for bad ductwork and bad filters. What's the condition of the wiring? Do I have signs of moisture? Do I have electrical problems? Overall, the condition of the wiring tells me a lot about how the equipment was installed and maintained. In this case, it's relatively clean. I don't have any worries here. Take the indoor blower motor amperage. While it's not accurate with the door panel open, it's still a good idea to get an amperage reading. Even with the door open, an experienced tech will see if it's way too high. In other words, I'm looking for bearing issues. I'm looking for any reason mechanically why that blower motor cannot handle the airflow that's required for the unit. If you suspect a problem, retake the amperage with the panel shut. Okay, and there's easy ways to do that. You can actually hold this panel, the front panel that you pulled off, and you can put the top of it right there, and you could sort of balance it against the unit. It will suck in, and you can take your readings here, okay? So again, with the panel for the blower compartment way open, your amperage will be a little bit different than with the blower closed. Okay. Next thing you're going to do, you're going to put the front of the unit back on. You can see here I have the front of the unit back on. Okay, I've put a temperature probe into the supply duct, and we don't have a return duct on this system. It's up on a stand and the air goes basically in this way. So I put a temp probe over the filter just as a place to put it. Okay, and it's not going to be perfect, but it will capture the majority of the air or the temperature of the air going across that filter. And I made sure I got it in far enough. The probe is actually going in far enough to not catch the bottom of that coil, okay, because I need to have it past the drain pan and actually in the airstream. Do I have a valid temperature split? Okay, if I look over here, I have a 63.4 supply air, 76.3 return air, which is a 12.9 degree temperature delta T or temperature split. Is this valid? Okay, can I tell without taking humidity into account? Remember, a good portion of cooling is the removal of humidity. So without taking wet dry bulb, is this right? Is this wrong? You really can't tell. So we have to look at a more accurate method. Okay, this is, again, using the same temperature probes that I already had in there because they do wet bulb as well. Okay, now we look at the return air relative humidity, 67.7%. Return air temperature, that's my dry bulb temperature. I have wet bulb temperature as well. Okay, and we manually set the airflow volume, okay, because I know my system is supposed to have 400 CFM per ton. This is a 2-ton system, so I have 800 CFM of air is what I'm supposed to have through here. We have supply air relative humidity, supply air temperature, dry bulb, wet bulb, okay? And the system calculates, this software calculates what my BTU per hour of cooling based on the readings and the airflow is. So as long as I'm getting 800 CFM of air, I am, with this humidity, I am actually cooling and using 23,432 BTU. Now, this makes a lot of sense. Okay, we have a 2-ton system, okay, which is 24,000 BTUs per hour. So I'm actually well within range of what my output and what my BTU capacity is. Okay, 23.4 compared to 2,400 for a couple-year-old system, not installed in the ideal conditions. It's doing what it's supposed to do. Okay, so we now can make some relatively large conclusions. We're rejecting heat to the outside. The outdoor temperature split is a little bit high. Remember back to the rooftop readings I took. The indoor coil is clean, and the temperature split based on the humidity is valid. The equipment is removing close to the rated BTUs if the airflow is correct. So our next step we're going to do is we're going to verify. We're going to do a little bit of verification about this airflow, okay, because the equipment appears to be doing what it's supposed to be doing from a refrigeration and a cooling and dehumidification. Okay, I'm going to take static air pressure, okay? I want to take air pressure after the filter, okay? And it's not going to be 100% accurate just on how I have to put this probe. The accurate way would be to drill a hole here into the unit itself, but I'm not going to do that. I want it to capture just simple, quick, dirty method. I have a return air pressure of negative 0.48 inches water column. Okay, now remember, my static pressure for this entire system, the rated static pressure is a 0.4. Okay, so I'm using almost above the full allowable static pressure for the system just on the return before the cooling coil, after the filter. Okay, so this is the static pressure that's being pulled through the system. That's pretty high. The return static before the filter is only a 0.08. So my filter drop, the static pressure drop across that filter, is a 0.40 inch water column, which is identical to the allowable external static pressure of this system. This is something important to remember. So we take a supply static with the filter in place. Okay, my supply static pressure is a 0.14 inches. So when we calculate total external static pressure, we use absolute values. Okay, so I had a 0.48 and a 0.14. So my total external static pressure is that 0.62. It's rated for 0.4 according to the data plate. So right here we're actually 1.5 times the rated static pressure. So I do have a little bit of an airflow problem, but remember what I said. We have an ECM blower motor in there. So the blower motor is actually ramping up, and you could hear this when we put the panel back on. Okay, the blower motor is ramping a little bit back up, and it's adjusting itself, and it's speeding up to try to pull enough air through that filter for my static pressures, for my ductwork, okay? Blower motor, ECM motors will self-regulate a little bit, but as they ramp up, they use more power. Okay, now, if I pull the filter, I get a return static of 0.16 without that filter in place. Okay, my supply static without the filter goes to a 0.16. So the total external static pressure without the filter is 0.32 inch water column, which is very close to the 0.4 the system is rated for. Conclusions based on static pressures. There's some restriction in the airflow given the type of filter being used. Some systems just cannot handle the woven or paper filters. You may need to use a looser filter. However, this is not a serious enough problem in this case to cause the excessive humidity in the condo or apartments. In this condo, I wasn't able to put pictures of it into this presentation, but in this condo, things like mirrors on the wall, outdoor windows, were just completely soaking wet. Water was dripping down them. So according to all readings, the equipment is running properly. So what's causing the high humidity? To move forward in this evaluation, we now have to jump outside the box. And what we mean by the box is the actual air conditioner. We need to move outside the box, and we need to talk about building air pressures and airflow. Okay, this is a simplified floor plan of a floor or portion of a floor in this condo building. Okay, we have a main hallway running down the center of the building. Condos of various sizes are in each side. Air will always move from an area of high pressure to an area of low pressure unless mechanical ventilation is involved. Hot air will rise, cold air will fall unless mechanical ventilation is involved. Common building exhausts in a high-rise building in a warm environment require mechanical ventilation due to the air being cooler in the individual units than outside. The natural exhausts will not work properly because, again, hot air rises, cold air falls. If I have a 95-degree day outside and my air in the building is 75 degrees, the natural exhaust is not going to work properly. These exhausts are straight ducts. They don't know whether or not they're supposed to exhaust or pull air in. Okay, it's based on building pressures and laws of airflow. Okay. Now, the other thing we have to remember in a large building like this is we have specific airflow and pressure designs for ventilation and smoke control. The main hallway is an emergency evacuation route. So the pressure, the air pressures in the main hallway is going to be slightly higher than in the individual units on each side. We want to, if there's a fire in, let's say, condo 2, we want to keep the fire and the smoke in that unit. We don't want it to spread into the hallway. So the way that these buildings are designed is that the main hallway has a slightly higher air pressure than the units. Okay, the fresh air comes into the main hallway from outside, and then because of exhaust and other stuff in these units, and I'll talk about it more in a second, okay, the air flows from the hallway into the units and then outside. That's how the ventilation works, okay? The main hallway gets the fresh air. Airflow in high-rise buildings is designed to keep escape routes smoke-free in case of a fire in that single unit. Ventilation air enters the building in the hallways and common areas and then moves into the individual units and then is exhausted to the outside through bathroom and kitchen exhaust fans. The individual units are at a slightly lower air pressure than the hallways or common areas. Anytime a door is open between the units and the hallway, you should always feel air moving out of the hallway into the units. If the unit has windows that can be opened or balconies, air should always move outwards. Between each unit, okay, either apartment or condo in a high-rise building and the common exhaust ductwork, there's most likely a fire damper. These fire dampers close in the event of a fire in the common area or the unit itself. The whole idea is to prevent smoke from spreading. If the dampers or mechanical ventilation fails, there will be no airflow out of the individual units because the dampers will always fail into the closed position. So going back to our little puzzle here, okay, this is a rough floor plan of this condo unit. Okay, we have the front door, which is up here. Okay, we have an open kitchen. There was an exhaust fan over here over a range. We have a living room and dining room, sliding balcony, sliding door to a balcony. The windows, other than that sliding door, cannot be opened. Okay, they're sealed. Master bedroom, closet for the master bedroom. Air handler was here again with a louvered door to allow the return air to come in. We have a bathroom That's the master bath over here, and a hallway bathroom, guest bathroom. Okay, both these restrooms had exhaust fans. They're mechanical exhaust fans. Okay, however, in a high-rise building like this, the mechanical exhaust fans will always be exhausting air whether or not they're running. If they're running, they just exhaust slightly more air. If they're not running, the air is exhausted based on pressures. Air comes in through the hallway from a crack under the front door and through a ventilation transfer grill that's over the ceiling. Air exhausts through 2 bathroom exhaust fans or grills. If the fans are running, additional air is exhausted. If the fans are turned off, the air is exhausted based on the building main exhaust fan. If the unit is at a slightly higher pressure, there should always be some air moving outwards through those exhaust fans. Simple low-tech method to check this. Turn the fan on and hold a piece of toilet paper near the fan. With the fan running, it should pull the toilet paper up to the grill. In this case, you can see it does not. This fan motor is turned on. There's no air being pulled up here. Use the same low-tech method to check the exhaust in any other rooms where there's exhaust. In this case, I found the fan does not pull paper towards the grill. There's no air movement at all with the fan running. There's no air movement at all with the fan turned off. So, at this point, we can make some conclusions. The building ventilation is not working properly. From the unit owner's or the renter perspective, their equipment is working right. There's a restriction someplace in the main exhaust path for this unit or the entire building. Possible restrictions could be the fire damper, a non-working rooftop exhaust fan, or some other collapsed ductwork someplace along the way. You don't know this at this point. All you know, based on the testing you did, is that the exhaust is not working properly. So, when we go back and look at what we just went through, was it the box or the building? In this case, the air conditioning is working perfectly. Has to be the building. Think outside the box. A basic understanding of ventilation, pressures, and airflow is required. We have to remember, humidity control requires proper ventilation. Okay, we have to have proper ventilation. You have to get rid of the humidity, or you have to have specialized equipment that can handle dehumidification in an enclosed environment. So that would be like a standalone or a tied-in dehumidifier. Okay, standard air conditioning requires that we do have some ventilation. It's what it's sized for. This equipment is not sized or designed to have a no ventilation area. Okay, so if we go back to some of our readings, okay, which readings which readings tell you the most? Well, really all of them. You have to take a look at humidity. You have to take a look at what's happening with the outdoor systems. Okay, and I'm going to try to find that picture again. You got to take a look at the operating pressures. Okay. We have to take a look at static pressures. Okay, got to look at static pressure. Got to look and see if airflow is working properly. Got to look at amperages. Okay, you cannot come to a conclusion without looking at all of this. And I guess that's my entire point. So again, in this case, the building maintenance team had to look further into it. I do know what the result was. There were 2 problems. One, someone had turned off the rooftop exhaust fan and not turned it back on. They had a big exhaust fan that pulled for the entire building on the roof. And the second problem is there was a closed fire damper for this unit. It had failed. The link had broken, and it failed into the closed position like it's supposed to.